Hi friends, welcome back to our series of sessions on sensors and transducers. Today we shall be discussing on the thermocouples. Basically, what are the principle of operation, what are the effects governing the thermocouples, and what are the different types of thermocouples, what are the different metals for thermocouples, and then what are the ranges, their characteristics, and the advantages and typical disadvantages. That's what we will be discussing in this thermocouple. So to start with, as we all know, thermocouple is an electrical device consisting of two dissimilar electrical conductors forming an electrical junction. The thermocouple produces a temperature-dependent voltage as a result of Seebeck effect. And this voltage can be interpreted to measure the temperature. So if you see the definition per se, thermocouple is just a temperature measuring device, which uses the measuring the temperature at one particular point. In other words, it's a type of a sensor used for measuring the temperature in the form of an electric current or EMF. Thermocouple consists of two wires, two dissimilar metals, which are welded together at the end, both the ends. The welded portion was creating the junction where the temperature is used to be measured. The variation in temperature of the wire induces the voltages. Then let's see the different effects. What we have, it basically depends on three effects: the Seebeck effect, the Peltier effect, and the Thomson effect. So if you see, the Seebeck effect occurs between two different metals. When the heat provides to any one of the metal, the electrons start flowing from hot metal to cold metal. Thus, direct current induces in the circuit. In short, it's a phenomenon in which temperature difference between the two different metals induces the potential differences between them. The Seebeck effect produces small voltages per Kelvin of temperature. This potential difference is proportional to the temperature difference between the hot and cold junctions. Then if you see the Peltier effect, which is the inverse of Seebeck effect, the Peltier effect states that the temperature difference can be created between any two different conductors by applying the potential difference between them. If you take two dissimilar metals, copper and bismuth, if we create a potential difference between two metals, heat flows from one junction to another junction. This is exactly what is called the, so it's actually the inverse of the Seebeck effect, where the temperature gradient produces the voltage, and if you induce the voltage, then the temperature moves from one point to another point, cold junction to hot junction. Then we have the Thomson effect, which states that when two dissimilar metals join together, if they create two junctions, then the voltage is induced in the entire length of the conductor because of the temperature gradient. The temperature gradient is a physical term which shows the direction and rate of change of temperature at a particular location. When a current flows through an equal heated conductor, heat is evolved or absorbed during the length of the conductor depending on the direction of flow of current. This effect is called as Thomson effect, which is reversible. If you consider a thick copper bar AB, whose both ends are maintained at the same temperature and the center is maintained at a higher temperature through some heating. When current flows through the bar from NA to NB, then it is found that the heat is absorbed at NA and is absorbed at the NB. Thus, there is a transfer of heat due to the current in the direction of the current. This is called the positive Thomson effect. The elements which are showing the positive Thomson effect are cadmium, zinc, and silver. Now let's consider if we consider the say bismuth bar under similar conditions. When the current flows in this bar from A to B, the heat is evolved at A and heat is absorbed at B. It's in the reverse of the thing. So this is actually the negative effect, where we have the transfer of heat due to the flow of current when it takes place in the direction opposite to the direction in which the current flows. And if you see the comparison of thermocouples, we have thermocouple type E, and where the two dissimilar metals are chromel at constant and temperature range is from -270 degrees to 1000 degrees centigrade. And then Seebeck coefficient, this is what we normally call it as the sensitivity, is 62 microvolts per degrees centigrade. And application environment, you can use it conveniently in oxidizing, inert, and vacuum atmospheres. Then we have a J-type thermocouple, where we have two dissimilar metals of iron and constantan. Iron is positive, and constantan is negative. It can be ranged from minus 210 to 1200 degrees centigrade. So typically it is used only 0 to 760 degrees centigrade only, where the sensitivity, static sensitivity at 51 microvolts per degree centigrade. And oxidizing, reducing, and inert atmospheres also it can be used. Then T-type is the most convenient and common thermocouple used in industry, which is made of copper and constantan, and the range is minus 273 to 400. This is the range where it is used mostly around 300 degrees centigrade. Sensitivity is 40 microvolts per degree centigrade, and it can be used in corrosive, moist, and even sub-zero temperatures also. Then the K-type thermocouple is another most common thermometer which is used, and the chromel alumel is the combination. The range is minus 270 to 1370, but it is typically used at minus 200 to 1260 degrees centigrade. Its sensitivity is also 40 microvolts per degree centigrade. It can be used only in inert atmosphere, not in corrosive and all these things. Then nickel, this is very rare, and B platinum is also an expensive type because it can go up to 1800 degrees centigrade. Usually platinum 30% rhodium and platinum 6% rhodium. So that's the plus and minus here, and it can be used comfortably up to 1800 degrees centigrade. But the Seebeck coefficient is only 1 microvolt per degree centigrade, and it can be used in oxygen because it's a platinum. So all the platinum based thermocouples. Then we have S-type platinum with 10% rhodium, and platinum where it can be used from 0 to 1480 degrees centigrade. So slightly it increases 7 microvolts per degree centigrade. Then R-type thermocouple, which is platinum with 13% rhodium, and then platinum, where it is one platinum is 13% rhodium on the positive side. So here also you can use it only up to 0 to 1480 degrees centigrade. Sensitivity will be 7 microvolts per degree centigrade. It can be used comfortably from the oxidizing and inert atmosphere. So if you see, basically you can categorize them as nickel alloy thermocouples and platinum rhodium alloy thermocouples. If you see the nickel alloy thermocouple, we have type T here, type 2, type J, type M, where they can be used comfortably. And this is the comparison between of the y-axis is millivolts, and then here we have the temperature in degrees centigrade. This is how the sensitivity also varies depending on this. Then you have platinum rhodium alloy thermocouples, right? Where we have different types, where basically it differs. As you see, this is on the higher temperature range compared to nickel alloys. And if you see the advantages, all the thermocouples follow the temperature changes with a small time lag, and they can be used in the applications where very rapid changes in the temperatures take place, and then conveniently respond to those changes very quickly. They're very convenient for measuring the temperature at one particular point in any apparatus or setup. And these also have some limitations because they have very low accuracy compared to resistance temperature detectors. And because of that, they cannot be used for high precision measurement. They have to protect against contamination to ensure long life, and they are placed at a very large distance from the measuring device, because all these are most commonly used in industries. Thermocouples along with RTDs find very, very common application in industry. So even if the accuracy is not that thing, it's okay, it's conveniently used in industry. So that's all about the thermocouples. And because we are placing them at a very large distance, it increases errors in the result. Okay, so that's all about the thermocouples. Hope you have enjoyed the session. So let's meet in some other video. Thank you very much.